All right. Hello, everyone. So my work topic is about the detection and curation of generated images from diffusion model, which is advised by Dr. Jianbo Shi and also collaborated with Jinxu Zhang, who I would like to express special appreciation to due to their helpful advice. So to start with, I'd like to first show some image generation examples, which is also directly related to my work. So today's deep learning models has already presented many remarkable abilities in the domain of image generation. So for example, we can not only generate high quality images, but also it comes at a high resolution, which is shown on the left. And also we can even combine the styles from two different images and it creates even more possibilities in the domain of image generation, which is shown on the right. And also here are some examples I believe everyone must have heard of, which is the Stable Diffusion. So simply by providing one line of text, you can generate images by yourself. And there are also numerous applications built upon that. So in this case, I have shown one example where we use the Stable Diffusion to perform the image painting task, which is shown on the right. So simply by selecting the area that you would like to replace with and providing the text prompt, you can generate a new image also by yourself, which is really amazing to me. So with all those remarkable models in generating the images, we can find one common characteristics, which is that they either from two of the model families, which are the generative adversarial network, which we call GAN, or the diffusion models. So considering all those models, it is natural for us to ask a question, which is that, can we tell if one image is fake or real? And it turns out that there are also there have been already many analyses conducted on the GAN-generated images, indicating the existence of fingerprints. And we call it a fingerprint because it can be captured as an important cue by the detector to differentiate between the GAN-generated images and the real image. And one of the well-known example is called the checkerboard effect, which is shown on the left. So as you can observe, if we zoom in to part of the GAN-generated images, you can find that it displays a checkerboard pattern of pixel arrangements, which is considered as a spatial artifact in the GAN-generated images. And also, there are some analyses conducted in the spectrum domain, indicating that the existence of spectral peaks existing in the GAN-generated images compared with the real image. So considering all those artifacts existing in the GAN-generated images, many various detectors have been developed with the hope that they can rely on those cues to make the image detection. And among all those works, my work is mostly motivated by two of them, which are proposed by Wang and Gragnello, where Wang has developed a universal detector to differentiate between a broad range of GAN family model images. And based upon that, Gragnello has further modified some layers in the model and push up the average detection accuracy to almost 95%, which is really amazing. So inspired by that, we like to extend the analysis from the GAN-generated images domain to the diffusion model domain, which we present the first work, which are called the image detection task. And inspired by the model performance in detecting the real versus fake images, we propose another work, which called image curation task, in which we try to explore if we can select the better image from all fake images generated by the diffusion model. So to start with, I'd like to first introduce the image detection task, which we aim to answer the question that can we tell diffusion model generated images from real image? And our initial thought is very simple. Since there are existing SOTA detectors pre-trained on the GAN images, what if we try to perform on the analysis on the diffusion model images? So in this case, we just take the four detectors from the SOTA detector pre-trained by Wang and Gragnello. And then we just collect a large amount of images consisting of 7 different models. So for the real images, we have selected the largest scale understanding data set with only the bedroom category as our only focus, since we want to reduce the unintentional bias across different data sets and also make consistency across all the models. And we have also included 2 GAN models, which are pro-GAN and style GAN, as a evaluation reference. And most importantly, we have included 5 diffusion models, which are the original denoising diffusing probabilistic model, and these 2 variants, IDDPM and ADM. And those models are used to collect images with the pre-trained model weight provided by the author, which also pre-trained on the LSU in bedroom dataset. And besides that, we have two more conventional diffusion model, which are the latent diffusion model and the stable diffusion version 2. And these two are used to sample images with the same text prompt, which is the image of a bedroom. And here is a table to summarize our dataset in the image detection task. So there are basically 7 models. 2 of them are the GAN and 5 of them are diffusion model. And due to the computational limits, we have only collected 5,000 images across each of the diffusion model compared with the GAN model. So to deal with this imbalance, we would randomly sample the same number of images from the GAN model during the model training and evaluation steps. And here are some sample images from our dataset. So as you can observe, simply by observing each of the images across different datasets, it would be really hard for our human eyes to tell apart if one image is from the real source or from the diffusion model generated. And yeah, so that's the experiments of our first model performance, which have 4 detectors, where 2 of them are from the wall. And based on the data augmentation, it is divided into blur plus GPG with 0.5 probability and 0.1 probability. And we have 2 detectors from Guadagnino, which is pre-trained on different datasets. And one thing from this table we can find is that both detectors have a good detection accuracy performance across the GAN-generated images. However, when it extends to the diffusion model, the detection accuracy would drop sharply to only around like 50%, which is equivalently to random guessing. So that tells us that the pre-trained detector is actually real bad at detecting the diffusion model, although it is highly proficient in the GAN-generated images. So that motivates us to further fine-tune the model and try if we can use the diffusion model as a guidance to make the pre-trained detector to be also capable of detecting the diffusion model images. So with that being in mind, we have selected the SOTA detector from the Guadagnino due to its superior performance in the GAN-generated images. And to do that, we just randomly sample 4,000 images across all the diffusion model and use the left 1,000 images for tests. And here is another table to summarize the fine-tuned model performance. And interestingly, we can find something from this table. So first, the general performance of the model will increase dramatically when it's fine-tuned on the diffusion model datasets. However, the degree of improvement might be different depending on the different fine-tuned datasets. So for example, if we fine-tune on the IDDPM datasets, we observed a large increase in terms of accuracy in the ADM and LDM datasets, but the improvements in the stable diffusion V2 and DDPM datasets are less. And among all those fine-tuned datasets, we observe the most improvement from the ADM datasets. And most importantly, we find that the model accuracy not only increases in terms of the diffusion model domain, but it also retains a high detection accuracy in terms of the GAN-generated images, which motivates us to hypothesize that there is indeed some common detectable features that exist among both the GAN-generated images and the diffusion model images, such that the detector can be trained to capture this as an important cue when making predictions. So to validate our hypothesis, we conducted 2 qualitative analyses, which is the T-SNAP realization. So in this, we just used the SOTA detector pre-trained from Guadagnino and then fine-tuned on the ADM dataset due to its best performance. And then we just extract the feature map from the loss convolutional layer, which represents the most high-level representation or understanding of the model. And then we just pass it to the T-SNAP for realization. And following the prior work in GAN-detected images, we have also conducted a spectrum analysis. So in which we just randomly sample 1,000 images across each of the diffusion model datasets. And then we just pass all the images through the high-pass filtering to extract only the dominant feature information. And then we calculate the average discrete Fourier transform. So here are the visualization of the T-SNAP. So as you can observe, before the fine-tuning, there is a clear distinction between the real image data points and the GAN-generated image data points, which is represented by the purple dots. However, when it extends to the diffusion model cases, the red dots, which is our real data points, has a high overlap between of them, which might explain why it has a better performance before the fine-tuning. But after the fine-tuning, we can observe a more clear distinction between the red dots and also the green dots, which represents the real images and the GAN diffusion model generated images. Although there is still certain degree of overlap, which we think is caused by the DDPM dataset, since our model also has 17% accuracy performance in that dataset. And most importantly, after the fine-tuning, you can still observe a clear distinction between the real images cluster and also the GAN generated image clusters. And here are the frequency analysis across all the datasets. So at first, we can observe some the dominant features from the GAN models, so those dots and patterns, which are also even more noticeable in the style GAN. But when it extends to the diffusion model, the patterns are less observable. However, we can still find something that is similar to the GAN models from the latent diffusion model and the stable diffusion, which we think is caused by the adversarial autoencoder architecture in those latent diffusion models that is similar to the architecture from the GAN model. So inspired by the remarkable performance of the detector in differentiating between the real images and diffusion image, model generated images, we propose another task which aims to answer another question. So can we tell which diffusion model generated images are better? And part of our motivation comes from the existing problems in the common diffusion model, which is that sometimes they can struggle at particular regions. So for example, when generating humans, the face or the hand regions are really bad. So here I have shown 4 image examples, which are generated by the stable diffusion using the same text prompt, a man sitting on a bench holding a cup of coffee. So as you can observe, the face quality across all the 4 images are pretty different. And for me, I would say the first image has the highest quality, while the second and the third one has observable artifacts. And so based on that, and also if you take a closer look at those images, you can find that the hands across all those 4 images are actually even worse compared with the face quality. So inspired by those artifacts, I would like to focus our analysis on the scope of only face regions instead of focusing on the multiple parts. And also, so based on that, we need to conduct a data set that is proper to our analysis. However, this seems to be a challenging task since we want to make sure that the images that comes in pair, such that we can make comparisons between them. And most importantly, we hope that those image pairs have similar context with only difference in the face region instead of other regions, since we hope the detectors can only learn cues and information from the face region instead of from other uncontrolled variables like the context or other parts. And to deal with that, we came up with a data generation method in a self-supervised manner, which contains mainly 2 methods. So in the first method, we utilize the idea of inpainting with face mask in different cover ratio. So in this case, the cover ratio is defined as the occluded area divided by the original mask area. So we generate this occluded mask through a simple script, which would randomly paint on the original mask, such that it was divided into irregular shapes in or multiple regions. And our assumption is that as we use this occluded mask, the image quality should get better when the cover ratio increases. Since in this case, with a higher cover ratio, that means the mask region is actually smaller, which would leave less artifact noticeable. And here we have some visual analysis based on the first method. So in the first column, we show 3 different original images. And from the second column across the last column, we have showed the impingement results with different mask cover ratio. Oops, sorry. So as you can observe, the image quality should generally improve as we increase the cover ratio of the mask. And the second method, we also utilize the idea of inpainting, but instead of using the mask, we decide to inpainting based on different image scale. So To do that, we have I have three examples shown on the below. So initially we have the full context, which means we just perform the inpainting directly from the original image. And then we have a 50% zoom in and 100% zoom in, which would focus on the regions that is more close to the face. So based on that, we hypothesize that the higher zoom in ratio based on the original image should produce better inpainting results because there is less noise compared with the full context, while it also can learn to capture the information from the regions that is around the face. So with these two methods, we can conduct our analysis. And our goal is to find the better image from the image pair, which is generated through our method. And the model we use in here is similar to the image detection task, which is also a resident 50 model. But in here, we made some modifications such that the last layer is changed to output dimension 2 to represent the two image pair. And also the adaptive pooling layer is changed from 1 by 1 to 1 by 2. So in this case, we can return a two-dimensional high dimension vector instead of 1, which only represents one image. And we have collected 10,000 real images from the Microsoft COCO 2014 datasets as our ground truth with a clear face present. And based on that, we do the inpainting at two different scales, which are 20% and 80%, to create the image pairs with different face quality. And based on that, and also we can cut the image pairs when it is inputted into the model, just to make sure or just force the model to look at both images at the same time instead of focusing on a broad range of images across different subjects. And it turns out the model could converge within 10 epochs with also a 89 validation accuracy, which is to our surprise. And here are some visual analysis that I presented. So as you can observe, the model prediction and the ground truth seems to align with our human objective evaluation. So for example, for the bottom left, where we shows a woman's head, as you can see, so it shows a better image quality compared with the original one. So to better evaluate the model understanding in terms of different image pairs, we have presented some analysis with the help of breadcam, which would highlight the regions from the image, which also seems to mostly affect the models when making predictions. So in this case, we have the original image pair for reference, and also the breadcam realization, which is shown on the right. So based on analysis, we find that the model usually has a high activation around the face region, which aligns with our assumptions, which means those artifact regions seems to play a role when the model making predictions. And also we have noticed that usually the model would have some activation around the hair area, which we think are classified as a high texture area with rich information, which might be an important cue to differentiate between the real and the generated images. But of course, it's the correct cases. And here we have shown some failure cases where the model performs badly or predicts the incorrect label. So across the realization, we have found that the model would usually have a high activation around the background or the closest area instead of the face region, which has a visible artifact. So based on that, we think it is due to the similarity between those areas, which also has some high texture region with rich information, similar to the hair or other parts in the face, that makes the model to confuse itself to incorrectly classify it as the better one. And so that also motivates us to, so that motivates us to propose the future work based on the image curation task. So specifically, we think that further fine-tuning on those hard cases could be conducted in terms of the image curation, such that the model has a better performance in differentiating between those rich texture regions, such as the hair in the closest and also the background. And then we think the model can be developed to detect more regions other than the faces. such as the human arms or the hands, which should be more challenging task in terms of the difficulty due to their spatial complexity. And also we hope to experiment with human labeled images, since in our cases, those images are generated based on some assumptions within painting. So with the human labeled images, we hope to evaluate more validated results based on that. And thanks. Any questions? Mm-hmm. All right.
That is like a generalized a lot of work. So I'm wondering if you're doing work with like Thesis, aren't you using a cumulative stages rather than using a university data?
Right. So so you're right that there's actually a lot of categories in the COVID data set. And when we deal with the COVID data set, we actually utilize the human face sample mask detection detector to curate those images such that there are clear face present. But like you said, we have also experimented with some already curated data sets, which is another one called human parts. So in that data sets, there are also clear face present, so we don't have to any further proper pre-processing. So yeah. Mm-hmm. Right. Right. Mm-hmm. It's fine. I see. So I'm not sure if the deep architecture from those fake images might mess up with our system. Since at least I can tell that we can use a detector that is trained on the real versus fake images to tell if it's fake. But like you said, I think it should be similar in the case where we can to make the, like, for example, the GAN generated images, which is classified as some numbers, 1, 2, 3. So we can do some adversarial trainings on that to make it incorrectly classify it at another number, right? Yeah. So I think, well, I can only see, I'm not sure if that's possible, but at least I think we can, there's approach for us to detect if it's from the real or fake. Yeah.